Let's say that we are running DDL operation for creating a customer table. As a result of it, the customer table is created, and in the next operation, what we do is we are inserting into the customer table two entries. And after running this DDL operation, again, two entries is added to the customer table. But what happens on the database side? Database saves the data into the hard disk, but in reality, database cannot directly save the tables into the hard disk. What database does is that the database uses the file system in order to save the data to the hard disk. So there are different kinds of the file systems. For example, NTFS is used in Windows, APFS for the macOS, and extended for Linux. So in our case, we will going to take a look at the example of the Linux in order to understand how on the very low level the tables are saved into the hard disk. So let's first take a look at the database, right? What is the database? From the point of view of the operating system, database is just another application. So for that, what the database does is database uses the file system to save data into the hard disk. So to sum up, a database is just a user program. It doesn't have direct access to the disk hard drive. So instead, it talks with the operating system, and the operating system uses the file system driver, for example, like extended for or NTFS, to manage the data physically. So the database uses normal files, and the most relational databases store data in the regular files managed by the file system. And each database has a directory folder, and inside that directory, inside that folder, so what we have is we have many files representing tables, indexes, logs, and the metadata. So for example, let's take an example of the MySQL, and more specifically InnoDB engine. So let's say in our case, when we are creating a database, let's say that our database name is my database, and inside of database we have created several tables, indexes, and so on, logs, and all of that data is saved into the in the file system as a separate file. So we are creating a my database folder, and inside of that folder, for each of our table, for example, let's say for customers table, we have a separate file. For example, in our case, the customers with the extension IBD, right? So that's what happens on the file system level. But let's take a look at the from step by step what exactly happens from the time that we are creating a table to the time when the zeros and ones are saved to the hard drive. When we create a table on the file system side, as we have seen earlier, the corresponding file is created. So for example, in our case, let's say that for the customers table on the file system side, the customers.ibd file in the extended for file system in the Linux file system is created. In the database side, database doesn't care about the physical layout. So from the database side, what it sees is it only sees that on the file system side that the file is created. So to sum up, what happens is when we create, for example, customers table on the file system side, customers.ibd file is created as a place where the data from the customers is stored. So the next step is that what happens to the table file, right? So we have a table. From that table, we have created a file, and what happens to that file? How exactly we are storing that file? Well, that file is divided into pages. The table in the file is divided into fixed size pages. Usually in most of the engines, for example, in InnoDB, at least in the InnoDB, it's a 16 kilobytes. So we are dividing that file into the 16 kilobyte pages. So each page is stored in the multiple rows. So for example, let's say that we have a table with the thousands of rows or millions of rows. So for each row, let's say the 20 rows, or whatever let's say that the 20 rows is 16 kilobyte, right? So then those 20 rows is divided into one page. The next 20 rows is divided to another page, and so on. So in our case, let's say if we have a 60 rows, those 60 rows is divided in that file. So in that file, in the customer's file, we have a 60 rows, right? Those 60 rows are divided into 3 pages. We have now pages, and let's see that how the pages are organized. So for that, B-tree data structure is used. So for example, let's take a look at the step-by-step. So what happens is that the pages are logically arranged in the B-tree data structure for the fast lookup. And leaf nodes, they are actual pages with the rows, and with the rows, and the internal nodes, they are keys and the pointers to the child pages. So for example, in this case, we have, for our case, right, let's say that we have 100 entries, and for those 100 entries, the way they are organized in the B tree as following, right? So we have, it's basically a binary tree. So from 1 to 50, it's a left node, and from 51 to 100, it's a right node. And from 1 to 50, they are divided into the pages. So because the 20 rows, we are separating into the one page. So we have the from 1 to 50 stored in the first 3 pages, and the subsequent from 51 to 100, they are stored into another 50 pages. So why we are organizing our data into B-tree data structure? The reason is for the fast lookup, right? So when we create a table, what happens is that the one index, clustered index, is created, and it's based on the primary key. So based on the primary key, for every table, by default, at least one index is created. But let's say that we want to create another index. Let's say we want to create an index based on the first name or last name or date. So for that, a separate B-tree data structure is created specifically to store the index that table. So this is the one that is presented here. This is only for the primary key index. If we want to create for another field, or let's say for the several fields we want to index them, for them separate B-tree structure will be created. What's the next steps? Now we have pages and how the pages are stored, right? So the next step, right? We are going to one step further, and the pages are stored in the disk blocks via the file system. So what's that mean? So each page is written to the disk blocks managed by extended-for, and for the extended-for organizes storage into the inodes, block maps, and the disk blocks. If you haven't seen my previous video, in my previous video I put that into the details how exactly we are storing inodes and the block maps and the data blocks into the file system. So I would advise you to watch first that video, and after that it will be more clear what exactly inodes and the block maps means in terms of the file system. So the next one is, what we do is the database writes a page, and after that extended-for allocates one or more blocks for that page, and then after that what we do is we are mapping those blocks to the physical disk sectors. To sum up, for our case, what we have is we have a page which is usually 16 kilobyte. For a page, we have a file header, we have a raw data, we have indexes, and we have a page trailer. So what we do with the page, the file system saves that page, maps that page into the data blocks. For the data blocks, we have for example, if we have a 16 kilobyte and the data blocks are usually 4 kilobyte, we are mapping them into the four data blocks. So after that, what the file system does is it saves those data blocks into the physical zeros and ones, right? So for that, it uses the disk sectors on the SSD and stores them into the, for example, each block is also mapped to several disk sectors. So again, if you haven't watched my video for the file system, please watch that first, because there I put that into the in details how exactly data blocks are mapped to the disk sectors. So now let's go to the next one. In the next step, what we do is we do a journaling and the recovery. both the database and the file system have their own journaling system. So for example, for database, it's usually write-ahead log or WAL, or for the file system, it's extended for journal. So what happens is when we insert the data, the first thing is the database writes the changes into its WAL, and after that the WAL file is written via the extended for. So the extended for in turn also journals that write. So after that, if the system crashes, extended for restores the file's integrity, and then the database replaces the WAL to restore the logical consistency. So-called double layer journaling, that's the reason why the databases rarely corrupt the data even after the crash. So let's go and step by step see what happens again, right? Let's take a look at it one more time, what step by step happens when we insert the data into a table. So for example, let's say that we are inserting into a customer's table data. The first thing that happens that we have seen earlier, right? The first thing that let's start with the database engine. What database engine does? Database engine writes a row into a memory page, and also it updates the B-tree structure, and it also appends that to a write-ahead log. And the next one is that the page flash to the table file, in our case, to the customers.ibd. And from there on, the file system picks up, and what the file system does, it allocates data blocks for the page, it updates the inode metadata, and it journals the metadata changes. And the last one, for the physical storage, those blocks that are allocated on the file system side, those blocks are mapped into the physical sectors, and the actual zeros and the ones are stored. So now let's go to the next one. So far we have seen that why we are using the file system for storing the tables or for storing the indexes into the disk. But now let's see that the why databases sometimes may skip the file system. In some high performance cases, the databases, what they do is they use row block devices for faster access, bypassing the extended for or other file systems, or for specialized storage engines, for example, for Oracle ASM or PostgreSQL's direct IO. So what they do is they don't use the file system, and they directly go to the IO operations. Now let's sum up what we have learned, right? So from for the database storage, from the table to the disk blocks, and to storing into the actual SSD into zeros and ones. The first step is that the database engine, right? It starts from the database, which is just another application. What database does is database engine, it manages the rows, pages, it manages the B-tree data structure for indexes and the transactions. The next one is that for each table, a table file is created. It's a logical container for the pages. What are the pages? Pages are the fixed size units holding multiple rows. So as we have seen earlier, it may hold, for example, from 1 to 20, depending on because each page is 16 kilobyte, and depending what is the size of the row, it may contain from 1 to 20, 1 to 30, and so on. The next one is that the B-tree data structure, it's a logical structure for fast row lookup. So by default, for each table, we are creating one clustered index where it stores that where the primary key is used for the indexing, and if we want to add more indexing, for example, if we want to add the indexing for other columns, we are creating another index, and for them a separate B-tree data structure is created. So after that, what we have a file system, and it maps the pages into the disk blocks and the maintains journal. And the disk blocks, what they do is they are mapping those disk blocks, the file system, what it does, right? It maps those disk blocks into actual sectors, and the sectors is a physical storage. It stores the zeros and ones.